Hello, today I want to show you how we can control an I2C sensor with our nRF54L15 XIAO board. And when we're having a I2C communication, we connect our sensor always with two lines. This is a SDA line and a clock line. And the communication is always 8-bit, with the 9th bit is an acknowledgement. And the communication starts always with the start condition. The controller sends the start condition and ends with the stop condition. And when we're seeing how read communication, for example, is we're having here controller, which is our SoC, our nRF54L15 board, and the target, which is our sensor. First, the controller. In earlier time, it's also master and slave, the names for this, but nowadays we're using controller and target. And the controller starts with the start condition. Then when it wants to read out something from the sensor, it sends the 7-bit address and also a 1 at the 8th bit, or at the first bit, actually, when you seeing it from the most significant bit first, and then we're having our 8 bits, which is sending. So this is a read command. We get the acknowledgement from the target, and then the target sending the data until it's finished. The controller then acknowledges this and sends a stop condition. The write communication is similar, only that with the write, the controller starts with the start condition, then it's sending the 7-bit target address with the 0, and for the write command, and then the target acknowledges it, and the controller sending then the data which it want to send to the sensor. Also send the stop condition from the controller. Here is an example communication. You see how it looks like with an oscilloscope here. And this is communication with the LM73. You're seeing here the first bytes, the start conditions, the first bytes, and then the controller as sensor sending 2 bytes, which are temperature sensor, for example. We're using here from Adafruit's board with the MCP9808. This is a temperature sensor. You're seeing here's a connection. We're having the 2 lines, SDA and the clock line. And there are also 3 pins here where you can change the I2C address. But actually with our sensor, this for the default, they are pulled to ground. That this means these bits here are set to 0. We see this later in the datasheet, which I2C address we're having. And with the board also we're having already included the pull-up resistors here, so we don't have to take care of this either. How we connect now our sensor with the XIAO board. We're having here our ground, which we can use for the sensor, and our 3.3 volt connection here. And the pin 111 we're using for SDA. This is the default and the Devicetree, and the P112 is the clock from the I2C. And we connect it like this, the breadboard here. You're seeing here's the ground line, and here's the power line. And there we're seeing the clock line connected with the breadboard, and also the data line here. We're starting again with the blinky example. We're making a copy from this project and call it MCP9808. We delete the build, and then we open this in Visual Studio Code. I make here save this workspace also, so that I have here a workspace, and make first a build. After the build, the first thing what we have to do is to configure the prj.conf here to activate the modules for I2C. I activate here two things. First, I2C itself, and also for the print functions, the float point support here. So configure I2C to yes, and configure CB print F float point support here. Then we can go back to our project and searching for the source file application, the main. First, of course, we save this here, Control S, and now we can start to program. So the first thing what we have to add here is I2C driver header, and I add also two macros, one for the I2C address and one for the temperature register. And we're looking in the datasheet and we're searching for the address from the MCP. Then using here, the address is 0011, and then for the pin A2 and A1 and A0, which is all to ground, we're having then here also 000, which result in the I2C address 18 in hex code. And the register which we want to read out, I mean, this is the simplest way at the moment. We are setting the register pointer. Here we're having the register pointer, and we are setting it to the temperature register, which is bit 7 to 4, all to 0, and the bit 3 to 0, then to 0101, which is then 15. Then we can read out the temperature register. So in hex code it's 5, and there is later a function how to calculate from these 2 bits, bytes, which we're getting the temperature. Now comes a little bit a tricky part. We need the node label for I2C, and the question is what we are using here. And I define here the macro I2C node, and using dt node label to getting the node label from this. The question is how we found this. I'm using here I2C22, and the name which we find then out is a name which looking like this. And since we built this already, you can try to find it under the Devicetree here, the configuration, or you going directly into the Explorer, which is maybe a little bit more easy that you understand the structure. There is the build folder, and in the build we're having here the MCP9808 folder, and then we're going into Zephyr, and there is our Devicetree which is built. Yeah, it's Zephyr.dts, and when you're searching here for I2C, you're seeing here first the pin control, which is not so interesting for us. And when we're going, then here we're having I2C This is not the one which we are using. We are using 22. Yeah, you see also there are two node labels. You can use I2C then it's compatible probably with the other nRF54L15 boards when you're using the same pins, or you're using the XIAO I2C label. Yeah, you're seeing here this is a whole path from the device which we're getting, but you can either use I2C or XIAO I2C when you want to get the node. So I use there also my help macros for later for showing the string for the path here for the sources for the I2C label. It's not necessary to put it in, but it's always interesting to see if this is working. And in the next step, I define a device structure. Here an I2C device, I'm using device dt get from the I2C node, which I defined before, and store it in structure device. This is how we can get control to the I2C bus. And I need an uint8 buffer area. It's 2 bytes are enough for us. We are sending 1 byte and we are receiving 2 bytes later. So a buffer from 2 is here enough. This I can delete. I don't use GPIO here. And in the next step, I define this already. I explain it later. This is a function from our 2 bytes which we're receiving, how to calculate the temperature here. Yeah? This is a function which we use, MCP calculate temperature. Yeah? Also defined it before. We find it in a data sheet, and I will show you later where it's standing. Then the first thing in the main is, this I can all delete, is we are defining our error variable, and I'm using here the macro show define just for the first time that we're seeing the I2C node. This I can remove. We're using the printf function. I don't use the log function since it makes it too complicated for this example. Yeah, so I'm using here printf. And the first thing what you always have to ask if the device is ready, yeah, if there's no error. And so I'm asking if the device is ready, and if not, then I print out an error and return the main function. In the while loop, also copy and paste here, the while loop here. What we are doing here. First, we defined in the I2C buffer on position 0 the temperature register. So we're doing first an write, an I2C write. Here with the I2C write function, we are giving here as first parameter the device, then the I2C buffer, and the I2C address from our device. And when there is an error, of course, writing an error message. And in the second step, I read out 2 bytes. Yeah? I'm using the I2C read function. Here again, the first parameter is the I2C device, then the I2C buffer, and I'm reading out 2 bytes. The address is again from our I2C device, from the MCP9808. And again, checking here if there's an error. And then I define the variable flow temperature, and I'm making here the MCP calculate temperature from the I2C buffer 0 and 1. And then I'm making a sleep from 100 1000 microseconds, so 1 second it's sleeping. So, and now we build our application, and there I found out actually you have really to be careful, yeah. When you build it already, and you have to check where, which folder you are here selected. When you selected this folder and you're making here a build, then when you're looking here also, I open a terminal and nRF connect terminal. You're seeing here it's starting the build from this directory. The build actually works, but not the underlying process for the special file which has to be built for the XIAO board, yeah, which transfer later the best flash on the board. So you're making changes, and the firmware itself doesn't get an update. So you have to select here the build, and then the whole process working like it should. So the folder, when you're seeing here also the nRF connect folder is now the build. Yeah? You can now look when you're making here the build, and then also the firmware at the end is built new. You see now also the merge text file is generated new, and when you're going now to best flash, now you're seeing here I have already connected the board, and using best flash, then the programmer which is using also the new version from the firmware. Yeah, we're seeing here flashing the merged hex file here in the build. And when I open now serial terminal on port 10, we're seeing here that I get the temperature. I'm making here a reset. This is the wrong one here. And you're seeing here also the node label, yeah, from the output. And you're seeing that the temperature is also changing. When I put my finger on it, it's getting higher. Yeah. So the question was still why we have to calculate here with this function, or from where to get it. And you're seeing it here in the datasheet. When the temperature TA is over 0 degree, then we are using this function for calculating the temperature. So upper byte multiplied with 2 to power 4, and the lower byte multiplied with 2 to minus power 4. And when the temperature is under 0 degree, we're using this function here. This is actually what this function here does. Yeah, we are calculating the temperature when the upper byte, so the flag is set that the temperature is under 0 degree, then we subtract from 2 power 8 since to a complement. Yeah. So you saw now how to communicate with an I2C sensor and the nRF54L15 XIAO board. Was a little bit confusing to find out the right node label. Of course, the nRF54L15 has more configurable ports there. So you have to check the device tree first, and you have to think about what node label you are really using, if you're using the I2C or the XIAO node label, or define even one by your own. Yeah, this was it for this time. See you in the next video. Bye.